Hello, everyone. Thanks for joining the seminar. So, a quick note about the Trustworthy ML Initiative. We are a group of people who are broadly interested in research encompassing trustworthy ML. It is almost a year for us running this seminar soon. And before we start today's seminar, I'd like to briefly introduce our initiative. So, our initiative has multiple goals. Firstly, we want to make it easy for everyone to access fundamental resources in trustworthy ML. Our website has a curated list of such resources ranging from introductory to advanced. We also want to provide a platform for early career researchers to showcase their work. In order to encourage discussion and debate, we have an active Twitter handle. So if you haven't already, follow us today. And lastly, we'll be organizing symposiums and workshops in the near future to strengthen our community. So going back to today's agenda, today's session is divided into two parts. We'll be having Shiori Sagawa's talk from 12 to 12:30 ET. And then we'll be having Vihari Piratla, and he will be giving his talk from 12:30 to 1 p.m. ET. We'll take a short break after that, and then we will reconvene for a participant-driven discussion, which will not be live streamed. So with that, without further ado, I would like to introduce Shiori Sagawa. Shiori is a third-year PhD student, and she studies robustness to distribution shifts. And to this end, she has already developed methods based on distributionally robust optimization and analyzed these algorithms in the context of deep learning models. And recently built a benchmark on distribution shift in the wild. She is a recipient of the Apple Scholars in AI/ML PhD Fellowship and Herbert Consul's Stanford Graduate Fellowship. With that, I would ask Shiori to take it away. Thank you.
Thanks so much for the introduction and for having me. Let me share my screen. Can everyone see my screen?
Yes.
Awesome. Thank you so much again for having me here, and I'm really excited to be here. Today I'll talk about improving robustness to distribution shifts. Standard machine learning models are trained under the assumption that training and test data are drawn from the same distribution. And under this IID assumption, as we all know, machine learning models have achieved high performance on a wide range of tasks. However, this assumption is often broken in the wild. The data distribution often changes from train to test time, resulting in distribution shifts. These distribution shifts can significantly degrade model performance in many real-world applications. For example, models are often trained on a few data sources, but with a goal of deploying it in many other settings. In autonomous driving, models may be trained on a data collected in certain locations, but they need to maintain high performance even when they're deployed to new locations. In another example, models can perform well on average, but systematically fall on groups of data underrepresented in the training set. State-of-the-art speech recognition systems work well for most users, but can perform poorly for Black speakers. Finally, models can latch onto spurious correlations and fail on examples where these heuristics don't hold up. When models are trained to diagnose pneumothorax, they can learn to associate the disease with its common treatment, test strains as shown here. And consequently, these models can perform poorly on the test X-rays with untreated pneumothorax, where there is pneumothorax, but no chest strain. All of these examples motivate the overarching goal of this talk, to improve robustness to distribution shifts. Concretely, we want to maintain high performance even when there are distribution shifts. This talk will have two parts. First, we'll consider a more idealized scenario concerning spurious correlations, and we'll talk about a method for mitigating this issue. In particular, we'll work with a classical technique called distributionally robust optimization and bring it to the modern regime with deep neural networks. In the second part, we'll broaden our view to other distribution shifts in the real world beyond just spurious correlations. And we'll talk about a benchmark of these real world shifts called wilds. Now I'll jump into the first part of the talk, which is showing work with Plummet, Tatsu, and Percy. As we've alluded to earlier, models can latch onto spurious correlations, which are misleading heuristics that work for most training examples, but do not always hold up. And to make this more concrete, consider a task to classify between water birds and land birds. Even if a model has good average error, it can be classifying the background instead of the actual object, relying on the fact that most training examples show water birds on water backgrounds. But this association doesn't always hold up. Water birds might be pictured on land, and the model would perform poorly on such examples. As another example, when models are trained to predict whether a person has blonde or dark hair, they can pick up on spurious associations with demographics such as gender. And these examples share a common structure. There is a spurious attribute that is strongly but not perfectly correlated with the label. To make this concrete, in the water birds example, the label is the bird type and the spurious attribute is the background type. And now we can split the data into 4 groups. In the majority groups of the training data, the spurious correlation holds up, but in the minority groups of the training data, the relationship is flipped. And when we train models by minimizing the average loss, the models perform well on average, 3% error in this case. But these models can pick up on the spurious correlations and fail in minority groups. And as a result, the model has high worst group error, in this case, 40%. In terms of the setup, we assume that we know these 4 groups a priori. And in addition, each training example is annotated with these groups and is composed of X, Y, and group G. At test time, we assume we don't have any group information. And what does this mean exactly? This means that we train a model that takes in X and outputs Y as usual, but the training algorithm can leverage group information. So our broad goal is to be more robust to spurious correlation, and we concretely aim to achieve low worst group error. So the question is, how can we train such models? Instead of minimizing the average loss, which we refer to as empirical risk minimization, we directly minimize the worst group loss. We call this approach group distributionally robust optimization, or group DRO. If you look at the group DRO objective, it simply computes the average loss for each group G prime, and then takes a max across all the groups. And now this minimax objective might look difficult to optimize, but we propose a simple stochastic optimizer and provide convergence guarantees. In each iteration, our optimizer first estimates group weights that measure which groups are the worst case, then computes the loss weighted by those group weights, and finally does a gradient update on the model parameters. In addition to the theoretical convergence guarantees, we also empirically observed that group DRO converges in a similar number of iterations as ERM. And now that we're ready to apply group DRO, how does it work in practice? We walk through the results on the face dataset introduced earlier, where we train a standard ResNet 50. Let's first look at the standard approach of ERM, or minimizing the average loss. As we discussed, this leads to low average test error, but high worst group test error. However, the training error is 0 both on average and for the worst case group. Comparing the test errors with the training errors, we see that the worst group test error is high because the model generalizes poorly on the worst case group. This has implications for applying group DRO. Group DRO controls the worst group error only at training time and doesn't improve the generalization issue. In fact, from the perspective of training error, the ERM models are already robust, achieving 0 worst group training error. With this in mind, ERM and group DRO are expected to yield roughly the same models. In fact, we observed that naively applying DRO doesn't solve our worst case error problem on neural networks. The worst group error is still high due to poor generalization. These are new challenges with respect to prior work on worst case performance and DRO. Prior works have largely focused on settings in which train and test errors were similar for the worst case group, as they work with small convex models or generative models. In these cases, naively applying DRO was effective. In contrast, we work with state-of-the-art neural networks, which suffers high worst group test error despite 0 training error. In this regime, naively applying DRO yields no improvement, as we saw in the previous slide. So how can we solve the problem that we have zero training error but high worst group test error? How can we effectively apply group DRO to neural networks? A classical solution is to regularize, for instance, via L2 penalty or early stopping. And this is a bit counterintuitive with respect to recent trends to train more complex, more over-parameterized models to improve average error. And yet we observed that when coupled with regularization, group DRO improves worst group error successfully. When we use strong L2 penalty, orders of magnitude stronger than the standard L2 penalty used for these models, training error is no longer zero, and the worst group training error is much higher than the average error for ERM. In addition, even for the worst case group, the generalization gaps are now small. Now, minimizing the worst group loss via group DRO leads to low worst group test error successfully. In this paper, we similarly showed on more tasks that group DRO with appropriate regularization improves worst group error, in particular for the waterbirds example and for the multi-NLI dataset, which is the NLP dataset. We also observed similar trends with other ways of regularizing the model, such as early stopping, in addition to L2 regularization. In summary, we have proposed group DRO as a method for mitigating spurious correlations and more generally distribution shifts across groups. To apply group DRO to neural networks, we saw that it is crucial to regularize models strongly, much stronger than we need to in order to achieve good average performance. And zooming out a bit, this is true not just for DRO, but also this is true not just for DRO, but any other technique that relies on weighting data in a special way. So this importance of complexity control is also interesting in light of recent works on overparameterization. Recent works have shown that overparameterization or directly increasing model size improves average error even beyond the point of zero training error. However, when it comes to worst group error, our results thus far hints that the opposite is true, at least in terms of model capacity. And in fact, in a follow-up work with Aditi, Panway, and Percy, we show that overparameterization indeed hurts worst group error. We also understand why this is the case, both through theoretical analysis and controlled simulations. In another follow-up work with Eric, Panway, Ananya, and Percy, we also studied spurious correlations in the context of selective classification. With selective classification, models can choose to make a prediction as usual or abstain. We might expect that this may help improve worst group performance since models can now abstain on out-of-distribution examples. However, when models are trained via ERM, selective classification can actually degrade worst group performance. In the paper, we characterize this phenomenon both empirically and theoretically, and we observe a nice connection with the group DRO work. In order for selective classification to improve worst group performance, the worst group performance has to be reasonably good, even without any abstention. And again, group DRO is a reasonable way to train such models. In fact, for group DRO models, we see that selective classification improves worst group error further. And that's it for the spurious correlation and method part of the talk. And now I want to switch gears to part 2, which is about the Wells benchmark for real-world distribution chips. This is joint work with many great collaborators from Stanford CS. We have Panway and I, Henrik, Michael, Weikua, Michi, Irina, and Tony, as well as Yuri, Chelsea, and Percy. We also have Marvin and Sergey, who work from robotics at Berkeley, Akshay and Anshul from Stanford Genetics, Richard and Emma, who study fairness at Cornell, Etienne, Ian, and Wei, who study agriculture, Burton and Imran from Recursion Pharmaceuticals, and Sarah, who studies conservation at Caltech. For this part of the talk, I want to broaden our attention back to distribution shifts in general, beyond just spurious correlations. As we discussed in the beginning of the talk, distribution shifts are ubiquitous in many real-world applications. However, real-world distribution shifts are underrepresented in the datasets used by the ML research community today. Most datasets were designed for the standard IID setting, and prior work on datasets with distribution shifts have largely focused instead on synthetic shifts and object recognition tasks. For example, it is common to modify images by changing their colors or adding noise, and in our own prior work, we simply cut and paste words onto different backgrounds. Other datasets split the data in ways that induce fairly extreme shifts, such as training a model in photos and then testing it on sketches. These existing datasets are important testbeds with well-characterized and clean shifts. However, they're not necessarily the kinds of shifts that typically arise in real-world deployments. To complement this existing work and to help researchers study real-world distribution shifts, our paper introduces WILDS. WILDS is a suite of 10 datasets capturing the type of distribution shift that ML models face in the wild across diverse application areas. To design WILDS, we talked to many domain experts applying machine learning to various applications. This uncovered many examples of distribution shift that they were grappling with. In medicine, models are often trained on a few hospitals, but must generalize to new hospitals. Similarly, in computational biology, models must generalize to data collected in new experimental batches. In agriculture, automatic analysis of crops across different regions, growing conditions, and crop types remain a challenge. And in toxic comment detection, models need to be accurate regardless of demographics. To address these challenges, domain experts have collected data on each of these tasks, and in WILDS, we build on these efforts by curating, adapting, and standardizing these datasets and bringing them to the machine learning community. These are the 10 datasets in WILDS. They include a wide range of distribution shifts that span diverse applications and modalities. As an example, let's discuss the IWildCam dataset. To motivate this dataset, consider an animal classification task for wildlife monitoring and conservation. In this application, images are taken by static cameras deployed in wildlife habitats, and models are typically trained on images from existing cameras and then deployed to new cameras. However, different cameras vary widely in background illumination, camera angle, and animal frequencies, and as a result, model performance can drop substantially on new camera deployments. This distribution shift is an example of domain generalization problem, where each camera is a domain, and the goal is to generalize to new domains at test time. As another example with a different type of distribution shift, let's go through FMOW. Consider a land use classification task on satellite imagery. Here, different amounts of data might be available from different regions around the world. For example, we might have more training data from the Americas than from Africa, and this could cause a model to do much better on the Americas than on Africa. This is an example of a subpopulation shift, where the test distribution is a subpopulation of the training distribution. Concretely, the domains, which are regions in this case, now overlap between training and test time, but what changes instead is their relative proportions. For subpopulation shifts, we typically assess models by their worst performance over all test domains. In addition to this subpopulation shift across regions, FMOW simultaneously considers domain generalization across time as well, seeking to generalize to future years. So the train and test splits include satellite images from before and after a certain time. Zooming out, the WILDS datasets consider shifts across domains, where domains are cameras, hospitals, experimental batches, and so on. The datasets fall into the settings we discussed: domain generalization, subpopulation shift, or a combination of the two. And for each dataset, we consider a setting that reflects the real-world challenges in the application. To quickly walk through the rest of the benchmark, we have Chameleon, which considers shifts across hospitals and histopathology. In RxRx1, we aim to generalize to data collected in new experimental batches in cell microscopy. In OGB-MUL-PCBA, we consider a molecule property prediction task, and we seek to generalize to unseen scaffold structures. In global WEHAD detection, we aim to detect WEHADs in images taken across many locations, time, and other conditions. In civil comments, the task is toxicity classification, and we want to be robust to spurious correlations with demographic mentions. In poverty map, the goal is to predict asset wealth across many countries and regions. And in Amazon, we consider sentiment classification across a diverse set of users. And finally, in the Pi 150 dataset, we consider code autocomplete and the shift across different GitHub repos and token types. Okay. To design models, we worked with many domain experts to identify and adapt datasets that fit the following criteria. First, as we've been discussing, the dataset should reflect a distribution shift that's likely to arise in the real-world setting. Second, the dataset should have enough leverage to train on robust models. We wanted our datasets to be non-trivial, but also tractable because models cannot be expected to extrapolate to arbitrary distribution shifts. To do so, we constructed each dataset to have a training set that comprised multiple domains with domain annotations and other metadata available at training time. Finally, we selected datasets on which the distribution shift caused a large drop in model performance, and I'll discuss this next. Concurrently, we trained standard models that measure the gap between their out-of-distribution performance, which is measured on the default splits and wilds, and in-distribution performance, which is performance without distribution shift measured on some held-out set. This gap reflects the extent to which distribution shift impacts the performance of standard models. As you can see, the gaps are large for all the datasets and wilds. In other words, these distribution shifts cause a large drop in model performance. The models shown in the previous slide were trained in the standard fashion via ERM, where we simply minimize the average training loss. However, we also found that models trained using more sophisticated methods also had similar gaps between in-distribution and out-of-distribution performance. Specifically, we benchmarked Coral and IRM, which are algorithms for the domain generalization setting, as well as Group DRO, which was developed for subpopulation shifts. On the domain generalization datasets, we found that these methods did not significantly improve over ERM. On civil commons, which is a subpopulation shift dataset, Group DRO helps, but there is still a room for improvement. And on the hybrid datasets, we found no improvement once again. This shows that these real-world shifts are still an open problem. We need new training algorithms and model architectures that can be robust to these types of distribution shifts. So if you're developing new algorithms and models, we encourage you to try out the Wells dataset. We have a leaderboard on our website, and we're accepting submissions. And in addition, to make it easier for researchers to develop algorithms on wilds, we've released an open source library. So with just a few lines of code, you can download a dataset, prepare data loaders, train a model, and then evaluate it with a standardized function. And in addition, we provide default models for all datasets, so all you need to do is to plug in your algorithms. The code paper and the leaderboard are available at wiles.stanford.edu, and please reach out if you have any questions or feedback. I'll end by discussing how we can build on and go beyond wilds. We've covered distribution shifts in 10 different ML applications, but these are really just a small sample of what's out there. In many important application areas, it was difficult to find a suitable dataset. For example, as mentioned earlier, prior work has shown that commercial speech recognition systems do poorly on some demographics, which made it a natural candidate for a subpopulation shift problem. But among existing publicly available datasets, we didn't manage to find a training dataset with enough demographic diversity. As another example, in medicine, one of the challenges concern the tractability of distribution shifts. For example, across time and hospitals, there may be changes in the relationship between the input and the label, and this might make it impossible for models to generalize unless they're given more information. For other applications, we found some candidate datasets, but did not observe a substantial drop due to distribution shifts. For example, in BAD 100K autonomous driving dataset, we found that if the training set includes both day and night images, then the object recognition performance is not that different between daytime and nighttime. And when we studied demographic fairness in stop and frisk policing dataset, we observed substantial performance disparities across demographic. However, we found that there are due to biases in the data rather than distribution shift per se. In our paper, we discussed several of these application areas in more detail and the challenges of finding suitable datasets in them, including case studies in the BDD and STF datasets shown here, the genomic dataset, and a couple of review datasets. Overall, the datasets and models are really just a start, and there is still a lot more that we as a community can do on the datasets front. And already there are many interesting open research questions involving real-world distribution shifts. For example, how can we characterize all of these different types of shifts and their effects? What kinds of algorithms will allow us to be robust to these shifts, and what leverage will they use? We hope Wilds will be a useful tool that encourages future work on real-world distribution shifts. And to encourage more discussion and future work around real-world distribution shifts, we'll be organizing a nearest workshop on this topic, where we hope to convene a diverse set of domain experts and methods-oriented researchers. So please check it out. And with that, I'll conclude by saying a big thank you to all the researchers that helped us along the way. And thank you so much for listening.
Thank you for the wonderful talk, Shiori. I think we have two questions. So Jacob asks that does some of this poor generalization come from the fact that the minority groups are underrepresented?
Yeah, so the poor generalization, comes from the fact that minority groups are underrepresented. So in the follow-up work regarding overparameterization with IIT Bombay and Percy, we studied why models generalize poorly on the worst case group, and the way in overparameterized models in the zero training loss regime, what we find is that if you learn the max margin classifier, then what we do is we first learn the core feature and then kind of memorize the minority groups. And that's why it generalizes well on the majority groups, but generalizes poorly on the minority groups.
Thank you. And then we have another question from Amy. And the question is, does this assume that you already know the groups? That is, which spurious correlations are the problem? And what do you do if you do not know which spurious correlations the neural network has learned?
Yeah, so in the group theory work, we assume that we know the groups a priori. So we know in particular, we know the label and in addition, the spurious attribute. I think there's been a lot of work trying to uncover the spurious correlations. And I think this is a very interesting and important direction because often we don't know what the spurious correlation is. One follow-up work that I was involved with, for example, uncovers these spurious correlations by looking at the failure modes of the ERM models. So you first train the ERM model, see which examples are misclassified, and many of these examples turn out to be minority groups, at least for this spurious correlation setting. So I think there's a lot of interesting work in this direction too.
Perfect. So I think with interest in time, we have another question from Sahil, but we would be glad if you can answer that question on the Q&A tool, and we can move to Vihari's talk then. So.
Okay, thank you.
So now I would like to introduce Vihari Piratla. And Vihari is a PhD student at IIT Bombay. His research focuses on problems that could enable wider reception of machine learning systems, such as their evaluation, generalization, and adaptation to new deploy environments. He is a recipient of the Google PhD Fellowship. With that, I would kindly request Vihari to take it away.
Hi, can you hear me? Can you see me?
Yes.
Right, let me share my screen. Can you see my screen?
Yes, you're good.
Is this Zoom window coming in? No, it's not. All right. Thanks, Chirag, for the introduction, and thanks a lot for having me here. I'll be talking about machine learning as a service and the research challenges that arise when catering millions of client distributions. Machine learning exceeds humans on many intelligent tasks. However, this superhuman performance comes at a cost. Training and deployment of such models is highly resource intensive. For example, automatic speech recognition systems are trained on hundreds of thousands of training hours and are computed on a high-end compute clusters. Also, the size of the models are ever increasing. And as a result, the state-of-the-art ML models are affordable only to a few resource-rich organizations. And this is where cloud machine learning APIs shine. Uh, they enable uniform access to the state-of-the-art machine learning models. And we see most of the technology companies are providing access to their machine learning models through the machine learning APIs across different modalities. And traditionally, ML models are trained and evaluated for a focused use case. If you wish to serve millions of clients through the service, several challenges stand in the way. We will look at two such challenges in this talk. The first concerns the training, and in classic ML, we train and test under the independent and identically distributed assumption. This may only generalize to the distributions that are identical to the train. But in Cloud ML, however, we are expected to generalize to seen as well as to unseen client distributions. So this is also called the domain generalization problem. The second challenge concerns evaluation. In classic ML, again, the models are evaluated with a single aggregate performance on a benchmark dataset or through leaderboard. For Cloud ML, however, a scalar performance on a benchmark is uninformative. And we argue that the performance should instead be reported as a surface over combination of client data characteristics. We will see what that means in a bit. First, let's look at the generalization aspect of the cloud machine learning APIs. This part of the talk will focus on our work in ICML 2020. As I have said, this problem is related to the domain generalization. And to understand what could happen if a model does not generalize to new domains, consider this example of automatic speech recognition. If the model is trained on native English speakers, it may not generalize as well to non-native English speakers. To quantify the same effect, we work with the Google Cloud Speech to Text API. And this API is trained on the order of 50,000 hours of speech examples. And when we tested it using the Mozilla Common Voice data, it gave an word error rate of 13% on US accents, but with the same content, but with a different accent, which now is Indian, we have almost double the error rate, which in this case is around 22%. So this is what happens if a model does not generalize to new domains, and that can have that can create a lot of inequality to the end users. And the domain generalization problem is about driving generalization to the new domains. And the problem setting involves training on multiple source domains and exploit the domain variation during the train time in order to generalize to new domains. For example, in a character recognition task, we might see the same character written in several different fonts. And we expect the model to generalize to the same character but written in perhaps in unseen fonts. The expected risk minimization based vanilla training algorithms does not generalize to new domains. And this failure mode can be, and one likely reason for this failure mode is due to the presence of domain specific features. And this illustration further demonstrates the same. Consider the feature space. The feature space can be broadly be thought of as constituting common as well as the specific features. The specific features are such that they are predictive of the label on only a subset of the domains, while they were either neutral or have negative label correlation on few other domains. Common features, on the other hand, are predictive over all the represented training domains. However, since you always deal with the max margin classifiers, they latch on to both the common and specific classifiers. And as a result, as we know, the specific features do not generalize beyond their respective domains. And even worse, they could hurt generalization to new domains. So an ideal domain generalizing classifier, therefore, should only look at the common features and should completely get rid of the specific features. And if you're wondering, the specific features does have some resemblance to the spurious features that Shiori spoke about. And there might be some differences, but I think the spurious features have come chronologically later. In the sense that they have introduced the spurious features chronologically at a later time. All right. So this failure mode of the expected risk minimization has motivated a long line of domain generalization algorithms. The perhaps the first one in this line of work is a Gannon et al. From 2016, where they propose to learn representations such that they are indistinguishable across domains. And the second line of work, which is more recent, proposes to called invariant risk minimization. It proposes to learn representations such that the per domain optimal linear classifier agrees across the domains. Both the ideas have influenced many follow-up papers and have been heavily studied in the literature. However, this invariant class of algorithms are hard to train, computationally expensive, and do not scale well to the large number of trained domains. Our objective is to design a simple algorithm that avoids the domain-specific features, just like any of these algorithms, but however is easy to train. We propose an algorithm called common specific decomposition, and we take the following approach. We decompose the softmax linear layer parameters for a domain D as a combination of common component and a specialized component, and the specialized component is further expressed as a linear combination of k-specific components. And the idea is to isolate the specific component of the classifier and recover the common component part and use the WC, which we are calling as a common component, as the domain generalizing classifier that we are hoping to identify. If we just look at this decomposition expression, there are many solutions to each of the WC and the WS. However, not every decomposition solution to this expression renders the WC to be the domain generalizing classifier we are hoping for. Then how do we identify the domain generalizing classifier? As we have looked at, a domain generalizing classifier contains no domain specific components. And so we go on and further emphasize our intuition and assert that WC should be orthogonal to the span of the WS. The WS being the span of WS being the orthogonal, being the domain specific components. This we call as the identifiability condition on WC. As we have already stated, the specialized domain specialized component is a linear combination of k specific components, and then the question arises: how is this value for k chosen? Let's look at what happens when we set k to the two extreme values that it can take. When we set k to the least possible value, which is 0, we effectively use no domain specific component. This is same as the ERM baseline, which we know does not generalize as well. And when we set k to the maximum possible value, common component is effectively free of all domain specific components. However, the estimate of WS can be noisy. According to the theorem 1 of our paper, which is marked here, the closed form solution of WC is a function of the pseudo inverse of WS. This makes the WC estimate also unstable when the WS is noisy. For more details, see theorem 1 of our paper. So k should be set to neither of these extreme values, but it should be set to a small value which is greater than 0. So let's bring in all the details together and make a dry run over of our algorithm. We start by choosing K, the number of specific components, the only hyperparameter of our algorithm. We initialize the common and specific classifiers and domain-specific combination weights, gamma I. The common classifier should be orthogonal to the span of specific classifiers, as we have earlier looked at the identifiability constraint. We impose that. And the classification loss is imposed using the specialized classifier and, and using only the common classifier. The, the classification loss that uses only the common classifier emphasizes the shared nature of the common classifier further. Finally, for use during the inference time, we return the common classifier, and this is the domain as our solution for the domain generalizing classifier. As you have seen, our algorithm is quite simple, and let's take a look at some results. Shown here are the improvement over the ERM baselines on a speech task for varying number of trained domains, shown on the x-axis. We go from 50 to all the way to 1,000 number of trained domains. And here we are comparing in blue with the previously best known solution on this data set. And the shown in green is our solution CSD. And CSD consistently performs better than ERM and CG over a range of number of training settings. We also evaluate on lipid K and Nepali C. Both of them are image tasks and handwritten character recognition tasks. And again, we are showing accuracy gains over the ERM baseline. And we compare here with the 3 other contemporary strong baselines. And the massive fear is comes from the class of domain invariant representation algorithms. And again, CST, which is marked in green, consistently outperforms other baselines on these 2 datasets. So we looked at a simple and an efficient solution to domain generalization called CST. Our solution has a runtime of only 1.1 times the ERM baseline. And our solution is also practical and easy to implement. It only requires modifying the final linear layer. And it scales to a large number of trained domains, as we have demonstrated with the speech task. Now we will switch gears and look at the evaluation aspect of the cloud ML that we have. And this is the second part of my talk. And here we'll be focusing on our under review work. Right. So as we have motivated in the introduction, we would like to go beyond reporting accuracy as a single aggregate number. Right. And more precisely, we would want to be able to answer how good is your service on my data. So in order to identify, in order to characterize my data, the first step is to identify interpretable and defining attributes of client distributions. And these attributes are chosen manually by a server or a mediating service. And we expect them to be task specific. For example, in an automatic speech recognition service model, the relevant attributes could be the background noise type, the accent, emotion of the speaker, input device, etc. And with the attributes such, we will be able to make user queries as shown in this table. For example, if I expect to use the ASR system in an Indian coffee shop, we would set the background to the noisy, accent to Indian, emotion to any, and gender to any. And then we would obtain the expected accuracy for my use case. And similarly, if I'm hoping to use the ASR service for assisting me with the 911 calls, let's say, then we set the background to street and accent to US and emotion to distressed. And again, get the expected accuracy corresponding to this use case. And notice when we get the expected accuracy through our specific use cases, they were much more direct and relatable than a single aggregate numbers on a benchmark data set. So this is what we are hoping to do. And if we define the attribute, in order to be able to answer the kind of queries that we looked at in the previous slide, the mediating service or the server needs to fill and report an expected accuracy for every combination of attribute value assignment. Right? Like in the earlier case, we looked at an ASR with attributes such as background, accent, and emotion. And we would then need to fill up this table corresponding to every combination of these attribute values. And, and owing to the resemblance to the Bandit literature, we will call each row here, which corresponds to the specific attribute value assignment to the attribute value assignment as an arm. And notice that this is a non-trivial problem because the number of attribute value combinations is combinatorially large. And this is where we step in helping with the estimation and filling this accuracy table with the combinatorially large number of rows. Right. So why do we want to look at accuracy surface again, beyond the motivation that we already have seen? Imagine a gender classification service. What typically happens is we report, it reports a test accuracy on as an average number, like this, like in this case, a single number. But beyond this, we don't see anything else. But take a look at what happens when we look at the arm accuracy distribution. And notice the spectrum of accuracies that we get. First, note that there is an arm for which we see an accuracy of only around 10%. We would like to know what it is. And there are 10% of the arms for which the accuracy is only slightly better than the random baseline. This is alarming. And a responsible service model should report the vulnerabilities of the service model if they wish to cater several use cases. And the point we want to make is the single performance number hides the model failure cases. And we should look at the accuracy surface and highlight also the model's failure cases. And accuracy surface can also be can be of direct utility to the user when the user wants to make an informed decision on which service to subscribe. Right. So now that hoping that you're all motivated for estimating the accuracy surface, let's look at how we can go about filling the accuracy surface table we looked at. And this is typically done by the server or some mediating service. And the accuracy surface estimating agency takes the following. We imagine the estimation to take this following pipeline. First, the estimating agency will define the attributes, and for each of the attribute also brings in the attribute classifier. We will see why we need the attribute classifiers in a bit. And, and also the estimation agency will also bring with her the unlabeled data. This is used as a resource for filling in the accuracy surface table. And at every instant, at every instant, the estimator will probe for an example X, and the human looks at the example X and provides observation on whether the service predicts the example X to be correct or not. And for the classification services that we look at, this observation is just 1 or 0. Zooming in on the estimator needs to do the following things for updating for keeping track of the accuracy surface table. First, the example needs to be mapped to the arm, to its corresponding arm. And the arm and the 1-0 observation is used to update the arm's expected accuracy and its uncertainty. And then the next step is to sample the next arm, and that further picks the next example, and then the loop continues. And this is notice that the example to arm mapping and the arm to example mapping that we discussed here are not readily available. Recall that we are dealing with the unlabeled data. This is where the attribute classifiers come in. And we do not expect the attribute classifiers to be strong, and they can be potentially also weak. So this makes the example to the arm mapping noisy. And when you put so many of these noisy classifiers together, then this mapping gets even more noisy. See our paper for more on how we deal with these noisy mappings. We would not be able to go over that in detail here. And we adopt a simple exploration strategy. That being, at every instant of time, we just sample the most uncertain arm. So we just focus on estimation of the arm's expected accuracy and its uncertainty. And and as long as we have good uncertainty per arm's estimate, we are good to go because exploration strategy is a trivial one. So in this talk, we will just focus on the estimation part of the system. Cool. So now we looked at the accuracy surface estimation. As you said, we need to look at the accuracy surface estimation model. And we have several examples and their corresponding observations. And as we have seen, examples map to their corresponding arms. And as a result, we have multiple observations for each arm. And we know 2 bits of information per arm. One is the number of examples per arm. And the second is the number of correct examples per arm, the C bit and the N bit. And since we need to keep track of the estimated accuracy and its corresponding uncertainty estimate, beta distribution is a natural choice. And a trivial modeling choice would be to independently track the mean and the scale parameter of each arm independently. And let's call this system where we keep an independent, where we track the parameters independently as the beta I. However, the independent parameters for each arm is not a good idea because there are combinatorially large number of arms. And moreover, we also have sparse supervision, so we wouldn't be able to estimate all the arms accurately with independent estimation per arm. So we make 2 observations that can potentially fix this problem. First, although the space of arms is quite large, the latent space of arms which affects accuracy we assume to be much smaller. And the parameters across the arms need not be independent, and they are assumed to vary smoothly between the arms. So to account for the 2 observations that we make the following 2 changes. First, we project all the arms through an embedding layer into a low dimensional space. And we tie the parameters of the beta distribution parameters between the arms using 2 Gaussian processes, one for the mean and another for the scale. The kernel for the Gaussian process is defined over the embedding space. And we can then go about estimating the embedding and the Gaussian process parameters through maximum likelihood objective on the observations. However, the gradient descent parameter estimation overfits on the observation. For example, consider the 3 arm setting here. We have 3 arms and their corresponding observations. And the first 2 arms are very sparsely observed. They only have 1 example each. And shown here is the fitted beta when you are estimating the beta parameters through gradient descent. And as you can see here, the mean of the fitted beta coincides exactly with the empirical mean. And there is barely any uncertainty even for the sparse observation. That is, the scale of the beta is also set to a very large number, tending to infinity. Overfitting, especially on the sparse observations, also affects the embedding because, as you can see here, the 2 sparse arms are said to have the mean value 1 and 0, although they were very confidently, although they have very sparse supervision. This in turn affects the embeddings that we are trying to jointly layer. We found that this happens because this overfitting behavior happens because of the gradient descent estimation. If you recall, in gradient descent, we revisit the observations multiple times. And every time we revisit, the same observation is treated as a new observation. As a result, the C1, the singleton observation on one arm actually is multiplied to several fold. And this is what was causing the overfit. But we could fix this simply by adding an additional supervision on scale of the arms. And this we found to have avoided overfit to a large extent. So as I said, we add a new observation to the pool of observations that the scale of the arms should reflect the proportion of the number of observations in that arm. So let's call this estimation model with this fix as a beta GPSLP. In order to evaluate how good now let's jump into the evaluation. And in order to look at how good the fitted accuracy surface is, we will look at the macro averaged square error between the estimated accuracy of an arm and its true value. So in our study, we evaluated and studied 4 servers. And shown here are two servers that are trained for animal classification task. One is trained on Cocos 10K and another on Cocos. The attributes here are defined to be scene revealing attributes, such as whether there is water or ground in the background. And the marked in cyan is the beta GPSLP, which is our final model. Oh, sorry, I forgot to mention the y-axis is the macro average square error, and the x-axis is the number of explored examples in both the plots. Notice that our system, which is marked in cyan, is far superior than the other two baselines. The story continues even with the two other service models that we considered. Here, the service models are trained on the task of gender classification, and one of them is trained on IMDb and another on CellerPay. So we looked at why accuracy surface mapping is an important problem. And our proposed system takes into account the varying noise level across songs. This is also called the heteroscedasticity. And we show significant gains over existing techniques. All right, so that brings me to the final slide. There are a few things that I would like to emphasize. The prediction services are crucial for bringing ML to masses. However, they could magnify the inequalities that are already present in the ML pipeline. Several research challenges arise when catering to millions of client distributions. We discussed two such challenges when scaling to the cloud in this talk, but many other challenges are yet to be addressed. Thanks for listening and thanks for having me here. I can take some questions now.
Thank you, Vihari, for the great talk. So we have a question from Abhijit. The question is it reasonable to expect the client to know the attribute combinations of their data before choosing the ML service?
Yeah, I think that's the starting assumption for us. As I have demonstrated with the ASR model. So the ASR model, and depending on, I know my use case, I know the emotion, and I know for example, if I'm dealing with a 911 service, I know the general emotion of the users who will be talking. And I know the general gender or any other attributes. So the attributes are defined such that the client will be able to tell me what his data is going to look like.
I see. Thank you.
Right.